we were going through exercises on divisibility and greatest common divisor. So in this next one we have two odd integers, both a and b are odd. We have to prove that a to the power 4 plus b to the power 4 minus 2 is divisible by 16. Since a comma b are both odd, we have a equal to 2n plus 1 and b equal to 2m plus 1 for some integers n and m. Now, what happens to this integer if we substitute for a and b these expressions? 2n plus 1 whole to the power 4 plus 2m plus 1 whole to the power 4 minus 2. We will now expand these things, these powers, using the binomial theorem. Now, while applying the binomial theorem, we of course would have to calculate the coefficients, which are nothing but the binomial coefficients. Now, if you find it somewhat not, I won't say difficult, but a little time consuming to calculate the values of the binomial coefficient using their definitions. For example, you want to calculate 4 choose 2. The definition says that it is 4 factorial divided by 4 minus 2 factorial times 2 factorial. In the numerator, you would have 24, that is 4 factorial, 4 times 3 times 2 times 1. In the denominator, you have 2 factorial times 2 factorial, which is 2 times 2. That means this is 6. If you find this way of calculating the values somewhat lengthy and time consuming, you can of course always use the Pascal's triangle to your advantage. So we know that these two slant edges of the Pascal's triangle consist entirely of 1s, and the inner numbers are generated by that rule, which says that, for example, the first row of the Pascal's triangle is just 1 and 1. In the second row, these are the outer numbers which lie on these two edges, slant edges. Now, this inner number is the sum of its closest neighbors in the previous row. That is 1 plus 1 is 2. So the next one is like that generated. So here this one is 3 and this one is also 3. 1 plus 2 is 3, 2 plus 1 is 3. And the next row is like that 1, 4, 6, 4, 1. So in this way also you can calculate the coefficients in the expansion of this power. This is your 4 choose 0, this is your 4 choose 1, 4 choose 2, 3 and 4. So we can now directly use these numbers along with the proper powers of these 2, n and 1 of course. So the first term is this. With 1 we don't write 1. After that 4 appears. 4 times 2 cube n cube. Then 6. 6 times 2 square n square. then again 4 times 2n plus 1, and here this number is also 1. So just like that we expand this second power also, 2 to the power 4 m to the power 4 plus 4 times 2 cube m cube plus 6 times 2 square m square plus 4 times 2m plus 1 and minus 2. So this 1, 1 and minus 2, they vanish, they give us 0. And what about the remaining things? 16n to the power 4 plus, let's write the similar powers together. There is no need to do that, but let's just write them in this way. 16 n to the power 4 plus 16 m to the power 4. So these terms you can see are already divisible by 16. What is the next one? 32 n cube. Like that, here also we have 32 m cube. Plus, okay, now so after fourth power, third power, the second power. The second power, however, is 24n square. Like that, here also 24m square plus, after that the linear terms 8n plus 8m. These are divisible by 16. Whether the remaining terms are divisible by 16 or not, that is not immediately apparent. We have to do something here for these other terms. Plus 16 m to the power 4 plus 32 n cube plus 32 m cube plus, here what we do, we write 24 as 16 plus 8 m square plus, here also 16 m square plus 8n square. We write that with 8n, like that 8m square plus 8m. So the expression now becomes this. Plus 16n square plus 16m square plus, we can now take 8n common out. Doing so, we get this factor n plus 1. In this last term also 8m times m plus 1. Now everything is okay except these two terms. They are divisible by 8. But what about by 16? Note that as an integer, n is either even or odd. If n is even, then n is divisible by 2, so this term would then be divisible by 16. However, if n is odd, then n plus 1 is even. So no matter what n is or what n's parity is, whether it's odd or even, n times n plus 1 is always even, and as such this term is always divisible by 16. Just like that, this one is also always divisible by 16. Note that since this and these are both even. We have and 16 dividing 8 times m plus 1. Thus 16 divides this entire thing, that means 16 divides this. Okay, so here the solution ends. Then exercise 8. Prove the following. This one has two parts. Part A. The sum of the squares of two odd integers is never a perfect square, cannot be a perfect square. And part B, the product of four consecutive integers is 1 less than a perfect square. Is one less than a perfect square. Okay, so let us see the solution. It is said that the sum of the squares of two odd integers for any integers n and m we have 2n plus 1 whole square plus 2m plus 1 whole square. So this is a sum of squares of two odd integers. If we expand these powers, we get 4n square plus 4n plus 1 plus 4m square plus 4m plus 1, which is equal to 4 times n square plus n plus m square plus m plus 2. Since this integer is of the form 4k plus 2 it is not a perfect square. If you are wondering why that is so, recall that, okay, what is a perfect square? Perfect square is the square of an integer. Now, an integer is either even or odd. So accordingly, if you take the square of an integer, it will be of these two forms. If the integer is even, let us see it here itself because it's not that big. If your integer is say even, if it's of the form 2 alpha, where alpha is some integer, if you take its square, you get 4 alpha square. But if your integer is odd, it's of the form 2 alpha plus 1, if you take its square, you get 4 times alpha square plus alpha plus 1. So whether you square an even integer or an odd integer, it's always of the form either 4k or 4k plus 1. It's never of the form 4k plus 2. And from division algorithm we know that these forms are mutually exclusive. Mutually exclusive means, I should not say mutually exclusive. What I am trying to say is that if any integer is of one of these forms, then it is not of the other forms. That is because, you see, integers of this form leave the remainder 0 when divided by 4. Integers of this form leave the remainder 1 when divided by 4, and integers of this form leave the remainder 2 when divided by 4. So squares, perfect squares, always leave as remainder either 0 or 1 when divided by 4, but never 2. So that's why this cannot be a perfect square. We have mentioned about this thing before. I mean, in the beginning videos on number theory, we have mentioned this. So that is part A. Okay, now what about part B? In part B, we have been asked to show that if we take the product of 4 consecutive integers, then that is 1 less than a perfect square. So let's see how that is true. For any integer n, we have product of 4 consecutive integers. Note that these integers we are considering here, no, n, m, here n, they can be negative also, keep that in mind. It's not necessary that they are positive, they are any integers. And just like that, this n can also be negative. It does not matter. These are 4 consecutive integers and this is their product. Okay. Now what we do, I think it's better to write the calculation not like this but like this. What we do, we keep n and n plus 3 as they are, and we change these two things. These two things means we don't change n plus 1, but we change n plus 2. In its place we write n plus 3 minus 1. Let's see where this takes us. Okay, now if we multiply the terms out, keeping n plus 3, then we get n times n plus 3 plus n plus 3 minus n minus 1. So this n and minus n, they cancel out. 3 minus 1 is 2. Now we multiply. So we get square plus 2 times n plus 3. So you can see that we almost have a perfect square involving these terms, but we are just missing 1. So we add 1 and subtract 1. So clearly this now becomes n times n plus 3 plus 1 whole square minus 1. So that's how this product of 4 consecutive integers is 1 less than a square. And here the solution ends. So then from here itself we can write exercise 9. Establish that the difference of 2 consecutive cubes is never divisible by 2. If we just simply generally think of elementary number theory, it doesn't seem like much that we have the division algorithm, we have the notion of prime numbers, composite numbers, and things like that. But in spite of this seemingly simple nature of the system of integers, there are so many things yet unknown, and the biggest mystery is the distribution of prime numbers. So here itself your life will be over if you just think of elementary number theory, that's all. You don't have to go to group theory, algebra, analysis, you don't have to go to those things. Your entire life will be spent on a small topic in elementary number theory. And also because number theory is almost as old as mathematics itself, so it's the largest, okay, among all the subjects we have in mathematics. This is arguably the largest. Okay, so now we have to prove that if we take the difference of 2 consecutive cubes, then it is never divisible by 2. That means it's not an even number, it's an odd number. That's what we have to prove. For any integer n, we have, so difference of consecutive cubes means n plus 1 whole cube minus n cube. So if we expand this, we get n cube plus 3n square plus 3n plus 1 minus n cube. So that means n cube plus 3n square plus 3n plus 1. From the first two terms we can take, okay, can we do such a thing here? I mean, can we factorize this? No, what the hell? N cube does not appear, only these things appear. Okay, so now what we do, we take 3n common out from the first two terms. So we have 3n times n plus 1 plus 1. Since, like before, n times n plus 1 is even, so this number, if you multiply this by 3, that is also even. Add 1 to that, it becomes odd. Is odd, and being odd, it's not divisible by 2. So this is not divisible by 2. That is understood. So we stop the solution here itself. Exercise 10. For a non-zero integer a, show that the greatest common divisor of a and 0 is the absolute value of a, then the greatest common divisor of a and a is also the absolute value of a, and the GCD of a and 1 is 1. Okay, this won't be that difficult. I mean, these things will follow very likely from the definition of GCD itself. Okay, so first we show that this is equal to this. Keep in mind there are one or two things here to note before we solve this exercise. A is a non-zero integer, so that's why this first greatest common divisor exists. Okay, and since it's only given that a is a non-zero integer, a may be negative also, but by our definition of GCD is a positive integer, so that's why we had to take absolute value of a and not just simply a. If you take, for example, if you have a equal to -1, you won't write GCD of -1 and 0 equal to -1. GCD by our definition is never minus, is never negative. Although in a slightly more general context than integers, GCD can be negative or can be something else. In our setup, in the system that we are in, we have restricted GCD to be positive, to be a positive integer, but this restriction has been placed only for the fact that considering negative greatest common divisors don't give us anything new, and it also Okay, I think what I am saying now, it may not be so clear. What I am trying to say here is that in the system of integers, we have a definition for the greatest common divisor. According to that definition, GCD is always a positive integer. In some general systems which are like integers but not exactly the system of integers, this restriction is not there. That's what I'm saying. And the uniqueness of GCD that we have of two integers or maybe more than two integers is not present in other systems. In integers also the uniqueness will not be there if we generalize the definition slightly, which however is not necessary here. Okay, and if these things are going over your head, just consider it as my rambling, nothing else. Okay, just forget about it. So let's now solve this. Note that the absolute value of A divides A and the absolute value of A also divides 0. Okay. Now, if D is a positive integer, if D is a positive integer dividing both A and 0, then D also divides the absolute value of A. Of course, every positive integer divides 0, but in addition, if it also divides A, then it will divide the absolute value of A as well. Why? Because if A is positive, then the absolute value of A is A itself. But if A is negative and D divides A, then from elementary properties of divisibility, D also divides minus A, which is the absolute value of A. Okay, so by the alternative definition, recall that we were able to, towards the end of this section, we were able to modify the definition of GCD slightly by replacing the condition B with some other condition. By that modified definition, this tells us that the GCD of A and 0 is this. Hence, if we want, we could refer to that result here, which however we are not doing. We know that this is also another definition of GCD, where the second condition involves divisibility and not the ordered relation. I think this last line, what I have said just now, this will ring a bell with you. We have already discussed about these things in the previous video. Okay, so this is the using the other definition of GCD. Like that, and I think there is no confusion about this divisibility. Absolute value of A divides A. Either this is A itself or it is minus A. So in any case it divides A. So here also we have this, and there's no point writing this 2 times because here the numbers are same. If you want, you can again write this, but it's pointless. Next we have this. Now if t is a positive integer dividing a, that means dividing a and a, then of course d divides the absolute value of a. Hence so these two are almost same. Finally, one of course divides a, one divides every integer, and one divides 1. If t is a positive integer, dividing both a and 1, then t is equal, d of course divides 1, and that is because d itself becomes 1, and this conclusion comes from the fact that d divides 1 and is a positive integer. This implies this is equal to 1. So that's the solution. Then another similar one, which shows that when we are calculating the greatest common divisor of two integers, their signs don't matter. Whether they are positive or negative, that does not matter. If a and b are integers, okay, in the exercise it's just simply said that if a and b are integers, then this and this happens, but I am putting this extra condition that at least one of which is non-zero, so that GCD exists. Not 0. Verify that GCD of A and B is equal to GCD of minus A and B, that is equal to GCD of A and minus B, which is equal to GCD of minus A and minus B. Okay. let D be the greatest common divisor of A and B, which exists because at least one of A or B is non-zero. It may be the case that both are non-zero, but at least one is non-zero. So from our main theorem on greatest common divisor, D exists. Okay. Since D divides A and D divides B, we have D divides minus A and D divides B. So that means D is a common divisor of minus A and B as well, just like it's a common divisor of A and B. Let C be a positive integer that divides both minus A and B. Then C divides both A and B. If C divides minus A, then C has to divide A as well. Now D is the GCD of A and B, and C is a common divisor of A and B. So C has to divide D. Thus, C has to divide D. So what does it tell us? It tells us that D is a common divisor of minus A and B, and also any common divisor C of minus A and B also divides D. Hence, D is the greatest common divisor of minus A and B. So that's how we get the first equality. And you can clearly see that the others will similarly follow. Similarly, we can prove that D is equal to the GCD of A and minus B, and D is the GCD of minus A and minus B. What I was saying there back then, which sounded like I was just simply blabbering about something, it's this fact. In the ring of integers, our GCDs are always positive, but according to the general definition of GCD, it is not always unique. For example, GCD of 6 and 3 is 3, right? But according to the general definition, which is not here, okay, GCD is minus 3 also. They are of course not the same thing. 3 and minus 3 are different integers, but in a sense they are same. They are associates in the ring of integers. In any ring, if you have two elements A and B, I should not say any ring but a special type of ring where GCD can be defined and exists. If you have found one greatest common divisor of A and B, then others also exist, and the others can be obtained by multiplying this GCD by the units in the ring. In the ring of integers, we have two units, 1 and minus 1. So if you get one GCD, there is another GCD. Okay, in general rings, you may get many more GCDs, which all of them are associates of one another. So essentially, there is no difference. Here, however, we are distinguishing between these two things, minus 3 and 3. For us, greatest common divisor is always positive. And if you don't know what rings and these things are, just don't bother. Exercise 12. Prove that for a positive integer n and any integer a, the greatest common divisor of a and a plus n divides n. So the greatest common divisor of a and a plus 1 is equal to 1. Because it's given that a is a positive integer and hence non-zero, so even if a plus n becomes 0, there is no problem. One of these integers is non-zero, so GCD will exist and it will be a positive integer. We know that the greatest common divisor divides both the integers a and a plus n. So this also divides a plus n minus a, that is equal to n. Okay, thus GCD of a and a plus 1 divides 1. Because GCD is a positive integer for us, it will be equal to 1, which implies in brackets we can write owing to the fact that GCD is positive, that this is equal to 1. So the greatest common divisor of any integer and the next one is always 1. They are always relatively prime. They won't have common prime divisors. Although we have not got to those parts, that is unique factorization, primes, prime factors, etc. But we will see that relatively prime. What am I saying? We actually have got this thing, no? Unique factorization theorem. So being relatively prime means they don't have common prime factors. So in their prime factorizations, the primes that appear will all be different. There won't be any common prime. Next. Given integers a and b, prove the following. Part A. There exist integers x and y. X and y for which c is equal to ax plus by, where c is also some integer, if and only if the greatest common divisor of a and b divides c. That is part A. And part B, if there exist integers x and y for which ax plus by is equal to the GCD of a and b itself, then the GCD of x and y is equal to 1. Okay. Solution. In part A, what is the thing we have to prove? We have to prove two things. First, c is some integer. Okay, consider c as some integer. Now, if we can find integers x and y such that this equation is satisfied, then GCD divides c, and conversely, if GCD divides c, then such x and y can be found. First, assume that there exist integers x and y such that C is equal to ax plus by, since the GCD divides both A and B, the GCD will also divide ax plus by elementary properties of divisibility. Which is C. Conversely, assume that this divides C, then C is equal to K times GCD of A and B for some integer K. Now recall our main result on GCD. If two integers are given A and B, at least one of which is non-zero, then their GCD exists and is of the form A alpha plus B beta. It's an integer linear combination of the given numbers of which you are finding the GCD. Now we know that there exist integers alpha and beta such that this is equal to A alpha plus B beta. So C will be equal to this K alpha plus P times K beta, that is for the integers x equal to K alpha and y equal to K beta, C is equal to ax plus by. So that is both the halves of the statement in part A. Now part B. If there exist integers x and y for which this, then GCD of x and y must be equal to 1. assume that there exist integers x and y for which this is equal to ax plus by. Now what we do, we know that GCD is a positive integer. It is not 0, so we can divide on both sides by GCD, and we write it like this. Okay, so in part A, what we have proved, that if you are able to express an integer as a linear combination of a and b with integer coefficients, then the greatest common divisor of a and b divides that c. Now in this case, that role is played by 1, the role of c. So by part A, okay, we will be needed to write something else also. We will write it in brackets. So this divides 1. Note that that's not what I should have written here. However, what I want to write here is GCD of x and y. There are some things to be noted. First of all, you compare this equation with this equation, but now instead of focusing your attention on A and B are now not the center of attention, but rather x and y are. These are some integers, and that is the second fact. These are integers. Note that these are integers because A and B are both divisible by GCD of A and B, because the greatest common divisor is a common divisor. So that means 1 is equal to an integer times x plus another integer times y. So by part 1, GCD of x and y should divide this c. However, there is one more thing. GCD of x and y will exist only when at least one of them is non-zero. If both of them are non-zero, then GCD does not exist. That, however, is not possible, because if both x and y are 0, did I say non-zero? If both x and y are 0, then GCD does not exist. That, however, is prevented by this equation. X and y both cannot be 0, because then the right hand side would be 0 and the left hand side is 1. So GCD exists, and hence we are able to apply part A. So by part A we are getting this. Within brackets we write, note that these are both integers. Also, x, y are not both 0. Hence, because GCD of x and y is by definition a positive integer, so it now has to be equal to 1. and that's how we get the part B, the second part. Then exercise 14. For any integer a, show the following. There are three parts. Part A, the GCD of 2a plus 1 and 9a plus 4 is 1. Part B, GCD of 5a plus 2 and 7a plus 3 is 1. See, if a is odd, here there is an extra condition, then GCD of 3a and 3a plus 2 is 1. Okay. Note that 2a plus 1, 9a plus 4, these integers cannot be 0. None of them in fact can be 0, no matter what a is. For the first one to be 0, a has to be minus 1 over 2. A being an integer cannot be that. Just like that, 9a plus 4 is also non-zero. So GCD exists at least. We don't have to bother about that. Okay, now our aim is to show that an integer linear combination of these two integers is 1. So in order to vanish a, what should we do? What we do is this: 9 times 2a plus 1 minus 2 times 9a plus 4 is what? 9 times 2a minus 2 times 9a is 0. 9 minus 8 is 1. Hence, by now from this equation itself we can write that the GCD is 1, and this follows from theorem 2.4. You go to this theorem and see what it says. So irrespective of the choice of A, these two numbers are always relatively prime. So now we know how to solve part B. Okay, for B, what should we do? We multiply 5a plus 2 by 7. Okay. 3 times 5a plus 2 minus 5 times what? No, that's not what I should write. 7a plus 3. 5 times 7a plus 3 minus 7 times 5a plus 2. 5 times 7a minus 7 times 5a is 0. 5 times 3 is 15 minus 7 times 2 is 14. 15 minus 14 is 1. So by theorem 2-4, this is equal to 1. C. Here, however, it's a little different. Since the GCD of 3a and 3a plus 2 divides both 3a and 3a plus 2, it also divides it also divides 2. Now 2 being a prime leaves us with only 2 options. Since it divides 2, it is either equal to 1 or equal to 2. If we suppose that this is equal to 2, then because this divides 3a, 2 divides 3a. This is not possible because a is odd. Since 2 is a prime, it should divide either 3 or a. 2 does not divide 3, so that means 2 has to divide a. That is, a should be even. However, it's given that a is odd, so our supposition is wrong. hence this must be equal to 1. Next exercise 15. If a and b are integers, not both of which are 0, prove that GCD of 2a minus 3b, okay, and 4a minus 5b divides b. Okay, hence GCD of 2a plus 3 and 4a plus 5 is equal to 1. Note that 2a minus 3b and 4a minus 5b. So 4a minus 5b minus, if we take 2 times 2a minus 3b, what do we get? 4a minus 4a, they cancel out, minus 6b, but we have one minus here, so that means 6b minus 5b is b. Since this divides both 2a minus 3b and 4a minus 5b, it has to divide this combination of them, that is b. So that's how it divides b. Then taking b equal to minus 1, we conclude by what we have proved that GCD of, you see, if you take b equal to minus 1, what happens to these numbers? 4a minus, I think I messed up, minus 5b. Okay, now if we take b equal to minus 1, this becomes 2a plus 3 and this becomes 4a plus 5. So we get this thing. And it has to divide b. So that means it has to divide -1. And so it also has to divide 1. This implies, because GCD is positive, that the GCD has to be in fact equal to 1. So here the solution ends, and here the video also ends. More exercises are there in this set of exercises, which we will solve in the next number theory video. And after that there is this section, Euclidean algorithm, where we learn an algorithm that uses the division algorithm repeatedly again and again, and that creates a situation which allows us to calculate the GCD of two given integers in a mechanical manner, in the sense that you can write a computer program for that. That's why it's an algorithm. So we will see these things in the next number theory video. And let me see the 24. So on 24th we would have our graph theory upload. We have already started the section on trees and forests, so we have to see further things on that. So see you in the next video. Until then, this is me, Lucifer, from A Mathematical Rule. Have a nice night.